Hello everyone, October 25th. All right, easy question today. Let's get it done as fast as we can. Mean stack. What does that mean? Have I done that before? Nope. Okay. Oh, okay. So for push pop top, retrieving the minimum element in constant time. Mean stack initializes the stack object. Push the element onto the stack. Pop removes the element on top of the stack. Int pop gets the top element of the stack, and get min retrieves the minimum element in the stack. I mean, we just need a stack and then keep track of the minimum value, and that's it, right? Okay. So let's. Uh-oh. I got it wrong. All right, hold on. I need to change this. I've done this in the past, so it's not. So we have a 265. Jesus. We're gonna change that into 25, right? 25 2021.py. All right. Okay, there we go. Mean stack. Yeah, we just need another variable. That's all. That's all it is. We just need another variable to keep track of the minimum value, and that will be it. So we're gonna have self.stack and self.min math.inf. We do need to go math then. Let's import math, and then push will be self.stack.append val self.min equals min self.min and val. Pop self dot. Oh, hold on. That's the problem. What if we pop the minimum value? Oh, it's not that easy, huh? What if we pop the minimum value? Let's see. If we pop the minimum value, how do we know what the next minimum value is? And then require constant time. Constant time. Hold up. Let's see. Push, get min. Right? Get min should be this. And pop, top, and get min. Wait, hold a sec. Well, we cannot use a single value because then we lose. Yeah, then if the value gets popped, then we don't know where the minimum value is. And they require everything in constant time. Hold up. Let's see. When we push, we have to keep a stack. How about the minimum? Can we do like a monotonic? Say a monotonic increasing stack? Still, it's huh. And I cannot use I mean, I can use a priority queue, right? So it's a stack and a priority queue. No. Priority queue won't work. because every time I pop, I can keep track on the min when I do push. How about a pop? Hold on, let's see. I push, -2, 0, -3, right? And I do keep track, so -3 is the minimum. Now I pop -3. Then what is my next mean value? Well, the next mean value, huh. I push and pop, remove element on top, get top of the stack, and get min retrieves the minimum element in the stack. So how do I keep track of, do we have to keep another one that have the value sorted? No, that's not likely. But how do we know which one is the smallest? If I pop the smallest. If I pop the smallest, how do I know get min shall return -2? I mean, I can solve, I think I can pass the test case by using a priority queue. But that's not what it's trying to do. Priority queue get min is not going to be, it's not going to be constant time. How do we do it in constant time? That's a good question. If we wanted to do constant time, min stack, push -2, okay. So the current min is -2, and I'm pushing 0, the current min is still -2. Now I'm pushing -3, right? Then -3 is smaller than -2, so I have to record -2 and change the min to -3. And when -3 gets popped, so I need something else to, hold on, if it's -2, then 0 pushes in, and 0 is larger than -2. Let's say I put it here. -3 comes in. But what if something that's in the middle? What's if like -1 comes in? We're talking about a sorted array. That's not constant time either. It's an easy question. There gotta be some easy way to handle this. Always be caught on that empty. Most 3 times 10 to the 4th. What the heck? Ah, that's the question. How do you maintain the min? We cannot sort. Can we sort? The value is 2 times 31st. That's too big. All right, we cannot sort. A dictionary, how does the dictionary help? So we push everything to the dictionary and also onto the stack. I mean, all we want to know, right? All we want to know is once a value gets popped, what is, like each value needs to have a connection, right? If I pop -3, if when I pop -3, if I know -2 is the next smallest, and then if I pop -2, I know 0 is the next smallest. But how do we get this relationship, right? And if we keep pushing values in, we don't know. When we pop, we have to have a stack to keep the order, right? And we need another mechanism to keep track of the minimum value. So if we have an increasing, so if something bigger, we keep pushing. If something smaller, then we pop. But that's not O1. What the heck? I have no clue. I have literally no clue. What's the trick? We have a hint. I might need to see the hint on this easy question because I don't know. I'm genuinely very curious on how we can keep track of the minimum value in O1 time. In constant time. Oh. Treat the minimum element in the stack. Wow. This will be a good data structure, right? Yeah, this will be a good data structure. I can pop, I can top get minimum value. Okay, so I pop the minimum value. I don't know which one to get. Alright, I'm gonna go look for the hint. I have no clue. Consider each node in the stack having a minimum value. Oh. So when we push in. Oh, I see. Oh. Prefix min. Ah, that's the trick. So we don't push in the value. Oh wow, I'm not in a good state today. If the value I push in, Oh my god. Oh my god. Then I pop. Ah. Yes. 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 Can't believe it. Wasn't not able to solve this one. Yeah. Yeah, it makes sense. It makes sense. Man, that's just. I think that's the 2 days in a row I wasn't able to solve. Holy guacamole. This is not looking good. Alright, so yeah, the idea is very clear. So I push, when I push to cell dot append, it's gonna be this. Oh. If stack, then gonna append value and the minimum value and stack -1, 1, right? Else self.stack.append val and val. Pop self.stack.pop, right? Top return self.stack -1, 0. Get min return self.stack -1, 1. And it is a simple question. It's just, gosh, yeah. How did I not get this? That is a good question. Name stack is not defined. Self.stack. Oh man, this is terrible. This is terrible. How many times I do this? Self.stack. Cumulative. Right? So, like, okay, I'm gonna submit this first. But, yeah, this is pretty bad. This is very, very bad. Alright, so, actually, I'm gonna put this in nightmare. But I wasn't able to solve it. Right? It's so ridiculous. So, I was stuck. That's rewind. Let's rewind what happened. So I saw this question. I was like, okay, we need a stack. That's fine. And we need to keep track of the minimum. So I have a minimum value. So every time a new value pushed in, I keep track it, right? And then I started writing that solution. And then I got stuck because when we pop the value, I know, okay, how do I know what is the next smallest value? So like, I have no idea. And I thought, oh, maybe we can do, priority queue or tree, but those are not all one time. And then I just got stuck. I was trying to sorting the thing, but it's not gonna work. So I was stuck on how to find the next smallest value, right? And it never occurred to me that we can do prefix min. All right, prefix min. So if you think from a different perspective, all we want to know is the minimum value at the current, minimum value of the current of the entire stack, right? And then when we pop it, we need to find the minimum value of the previous stack, right? The previous one. And then we keep popping, we just need to find the minimum value of every single step on the stack. So if we keep tracking the minimum value at the beginning, I was actually almost there. I was thinking about, okay, I have a minimum value at the start, and then when I push it, and I was trying to find the next. And now when we push it, we need to keep track of the minimum value of the stack. Wow. Very disappointed. Very disappointed. This is terrible. Alright. It's 155. Alright. Very disappointed that I needed a hint to solve this easy question. What eluded me was the concept of prefix min. Yeah, it's prefix min. Anyway, I mean, there's nothing more to discuss. It's very straightforward. Just a little trick. I should know, right? It's like prefix sum, or the prefix thing. All I was thinking about is range. Every time there's a range problem, I thought, okay, it's got to be a prefix. But this is not. This is not a range problem. Yeah. Yeah, the min stack. Oh, the min stack. Now I know what it means. Now I know what it means. All right, let's shake it off. This is terrible. All right, let's do another one. So I want to do the concurrency again. It's fun. Right? It's fun. So let's do this. All right, print full bar alternatively. Let's see how this one goes. I have 7. What the hell? All right, suppose you're given the following code. Oh, that's interesting. The same instance of foobar will be passed 2 different threads. Thread A will call full, thread B will call bar. Modify the given program to output full bar n times. There are 2 threads being fired asynchronously. One of them calls full while the other calls bar. It's being output 1 time, output 2 times. Nice, I like it. Let's try this one. This is interesting. So what we're gonna do is, this is 1115. 1115. Yeah, but there's no test cases because like I don't want to write test cases for this. How complicated it's gonna be? I have to write threads and stuff. So let's just copy this in. Okay, so there are 2 things, right? So one thing is we need to know how many times to print, and the other is the order. So it has to be, this one has to print first, and then this one print. Right, we need to pick a tool, right? Or pick a tool. Which tool are you thinking about? Probably semaphore, because semaphore has the values, right? So let's say we have a semaphore that's initiated to be n, right? So we're going to print n times, and when semaphore is 0, then we stop. Right? Let's read again semaphore. So semaphore threading. Let's go for semaphore. All right, let's see. So we can have acquire and release, and So release calls minus the number of acquire call plus an initial value. Acquire method blocks if necessary until it can return without making the counter negative. Without giving values to 1. The numbers of release calls minus the number of acquire calls, right? So the option gives the initial value at default to 1. So when I initiate it with a semaphore, it's decremented by each acquire call and incremented by each release call. When acquire finds that it is 0, it blocks, waiting until someone calls release. Can we use this? I I don't think so. No, I don't think we need semaphore. All we need is the synchronize, because the print number of times is right here, right? The number of times is right here. So all we need to do is to make sure this one prints first and signal this to print. And after this print, signal this to print. And this signal back. So just back and forth, right? So this one I can print and then I signal. And then this one will block here. And once this signal this to go, and then this will print. And once it prints, it will signal this to go. Okay, so it's not going to be semaphore. I think a lock might be sufficient. Let's see, a lock. It's a primitive lock, all right? One locked. A primitive lock is one of the two states, locked, unlocked. It's really an unlocked state. It has two methods, acquire. When the state is unlocked, acquire changes the state to locked and returns immediately. When the state is locked, acquire blocks into a call to release in another thread. So let's say I have a lock. I always import threading. Alright, let's say I have self.lock equals threading.lock. Right? So initially I don't do anything. Alright. Wait, do we need two locks? Hold up. Because this one, initially, I need to acquire. Hold up. How do I stop? I stop if and I signal this to go. All right, so this needs to acquire a lock, but it needs to be. But when we get the lock, it's in the unlocked state, right? It's created an unlocked state. Okay, so how do I block here? If this comes in and I say I acquire a lock, this needs to acquire a lock too. Huh. No, I want this one to be blocked first. Right? I want this to be blocked first. So something, when I get it, it has to be blocked. Maybe it's not a lock. Now it's not condition. I don't need condition. Semaphore starts as 1, which is also not locked. Is something that starts with locked event? Okay. Object manages internal flag. Blah blah blah. Set and a reset false. So the await method blocks until flag is true. The flag is initially false, so we can do event, right? So initial event is false. And then when it comes in, it's going to wait for it, right? So I'm going to wait for it here, because the initial event will be false. And I'm going to wait, because wait blocks until the internal flag is true. And once this is done, I'm going to set it to true. And then when I come back, I need to block here as well. Okay, how about two events? Two events. Okay, let's have two events. So I have events, right? Events might work. So event1 and threading.event2. So I have two events. Now when I come in, every time this has to go self, say self.events1.wait, right? We have wait. But initially it's all false. So this one comes in, I need to wait, so self dot. Oh, but initial is false. But anyway, when I print out, I need to say self.events1.set, right? .set. And then when I set, this one will go. Oh, it's true if only if the internal flag has been true either before the wait call or starts. So I print this and I say set, and this has been waiting, and then it print. Now after it prints, I need this one shall print and this one shall wait. So let's say this one wait by say events 0 dot wait, and after this print, I'm gonna say self dot events 0 dot set. All right, when it's set, this one go, and I will call this set. So after this set, self dot events 1 dot unset, right? Clear. So I clear. So I wait for it. Once I got signal to go, I go. And after I go, I signal the other one to go, and I block myself. And I come back, I block myself. And here, I come in, I will print, right? And then I'll, after printing, I'll set this one to go. But before I do that, I need to block myself, right? So let's say I need to dot clear, right? So on come in, this one will always be weighted because initial is false, right? So on come in, the two threads, this one will be, this one is blocked. This one will print, clear, and then set this, and then immediately this one is blocked. And then when it's blocked, this one gets clear, and it print. After print, it will set this, right? And then after set this, and it will clear. No, I should clear first. I should always clear first, because if I don't clear first, I set, right? And then this one will go, and this is my set. So I might go again. So I should always clear it first. So if I clear it first, it's guaranteed. Because when I clear, this line, this is still blocked, right? Because I haven't called set yet. So this is blocked, and I'm here. And this one ensures that I get blocked again. And then I call set. When I call set, this one will go, print again, right? I'll print again. And after print, I clear, so I shall wait. This one shall work. All right, let's give this a shot. Use test cases. Let's see. Yep, I think it's good. Let's say 10. think it's right. Yep, it is correct. Well, kind of slow though. So this is using events. Right, so this is using events. This is using events. Events is easy to use because I know when to call and when not to call. So it's using events. Go on 104. 27. All right, so now we solved it. Let's try to see. I mean, semaphore. No, I don't think semaphore. A lock, right? How about we use a lock? Well, if we use a lock, let's say we have two locks as well, right? I have two locks. So comes in, I want to acquire the lock. Because initially the locks all initially the lock is false, right? If you look at the lock, where's the lock? Condition r lock lock. The initial, when we do, the lock is unlocked. What does it say? It is created in the unlocked state, right? So if we do a lock, it's created in the unlocked state. And then foo can acquire a lock. I can acquire a lock here, and that will acquire, and I will print. And after I print, I will release the lock. Okay, so after print, I release the lock, which will cause myself to get blocked. No, hold on. I acquire the lock, and it's locked. And then I release the lock. And right, I release the lock, and then I signal bar to go. And bar, and then when I release the lock, I go back. See, that's the problem. I need to release. How should I do it with the lock object? I can release the lock. Because I can only wait, right? I can only wait if I start with acquire. So I will try to acquire the lock, and it's not been released yet. So I need to wait for bar to release it. And when bar released it, I will go in and I will print. And after printing, I still have the lock, and bar cannot get the lock. And bar is locked. I get the lock, and then I will release it. And once I release it, bar will go. Maybe one lock is sufficient. Hold on, think again, think again. I can just say with lock, right? And then with lock. And once we start, yeah, if we have a lock and both has with lock, then one of them will get it and the other will not. Yeah, hold on. This might be promising. Hold on. Let's try. It'll be easier to reason, I think. So let's say we have just a single lock, self.lock, threading.lock, right? And then when we come in, we just with self.lock. Both try to get it, right? So both try to get it initially with self.lock. So both try to get it. And because initially it's unlocked, so one of them will get it first. But then we need to decide if it's your turn to print. So we can say your turn, self.turn 1, right? So foo will print when the turn is 1, bar will print when the turn is -1. Oh, isn't that condition? Hold on, we can do that later. So if self.turn is 1, then we do something. What if it's not 1? Well, if it's not 1, then I release the lock, right? If it's 1, then I print this and self.turn -1. And here the same, we say if self.turn equals -1, then I print bar and then self.turn times equals -1. All right, let's see how this one works. All right, so once it starts, we don't know which one will get the first call, but that doesn't matter. So one of them will get the first call, and then we'll grab the lock, and the other one is blocked. And when we grab it, we'll see if the initial turn is 1. So if full gets it, perfect, I print full, and I set the turn to -1, and I release the lock, right? And when I release the lock, this one is currently blocked. So this one will grab the lock, and this one will get blocked, right? What if I release the lock, and this one is not ready yet? Let's say it's scheduled to go sometime later. Well, if this one released the lock and this is not ready and go back up, I will see, oh, self.turn is -1, so I cannot go. So I just keep going. So I keep releasing, grabbing, releasing, grabbing. And this one's going to work. I think this one's going to work. Oh, we shall call it full bar 2. This is full bar 1. All right, let's try this. I think this is going to work. It's not working. Oh, I see, because I already exhausted the for loop. Therefore, let's go condition. This is a condition. This is condition. So go back to condition. So we have a wait for, right? So wait for is only when this is, so with grab, what does a wait for do? Wait and to notify or until a timeout occurs. If the calling thread has not acquired the lock, it will release the underlying lock and then blocks until it is awakened by notify, right? So wait for will have a condition while not predicate we're going to wait. So we're going to wait for the predicate until the predicate is satisfied or into a timeout. Okay, so what the condition does is I'll grab a lock, right? So here is the grab. We'll grab a lock, and then I'm going to wait for the condition, which means I grab the lock and I release it immediately, and we're going to wait for this condition. If the condition is true, then what if the condition is true? The disfruté method may call, wait, and repeat it until the predicate is satisfied. Must be held when called and is required. The predicate is validated with a lock held. So basically it says I'm going to try to grab the lock, but if I can't grab the lock, it won't go inside. So I grab the lock, then I check, right? If it is good, if the predicate is good, basically it's this, right? If predicate is good, Well, not available, then I'll wait. If it is available, then I do this, then release the lock. If it's not available, I will wait, and then relinquish the lock. Okay, so I think it's condition. Self dot, no, not here. Self dot condition equals condition, right? And self dot full turn, right? Full turn will be lambda self dot turn. No, it's still, and we can just self dot turn equals 1, self dot bar turn equals lambda self dot turn equals -1. All right, and then self dot condition, and we say self dot condition dot wait for. We're gonna wait for self dot full turn. Wait for my turn. If it's not my turn, I will relinquish the lock, release the lock, and get blocked in the wait condition, right? And once I got signaled, I'll grab the lock. Oh, hold on. I had this yesterday, last time. So if I'm waiting, right? If I'm waiting and somebody signal me to go, what happened? Wakes up on the thread waiting for the connection. If there any waiting, and once awakened, we reacquire the lock. Okay, so when we notify me, I will try to reacquire the lock, right? I have to reacquire the lock. Yes, yes. So wait for. I don't think this is this. It's just wait for, and once it's good. So once I got notified, and notify will release the lock, right? Notify method wakes up. Wait, what does notify do? Wake up. If the calling thread has not acquired the lock, the method wakes up at most end of the thread, waiting for the condition variable. Current one wakes up exactly in the threads if at least some threads are waiting. However, it's not safe to rely. Waken thread does not actually return from its wait call until it can reacquire the lock. Does not release the lock. It's caller share. So I need to release the lock, right? So I'm gonna wait for it, and once it's my turn, I can say print, right? And after print, I set it to this. So this one will be the same. Condition, right? Let's say self.condition dot wait for self dot bar turn. And then we do this, and then we do this. Okay, let's analyze it. So initial condition is, I think initiate is not acquired, right? So whoever's gonna grab it first, well then we're gonna wait. So if full grabs it first, and this one will evaluate to true, so wait for is true, and it does not call wait. And we do this, turn it, and because this grab first, this one will be blocked at this stage. And then we'll turn this to -1, and they release it, right? Once they release, both will go into this condition, and one of them will grab it first. If this one grabs it first, the condition is not right. So this will, at the wait stage, it will wait here, and it will release the lock. And this one will go in, and then it will wait for this, and this is good because it's 1. It's -1, right? So it's -1, so it can go and then turn this and then release the lock. But this is still in a wait stage, so we need to also do self.condition.notify. There's only one, so we can just notify once. So I need to notify, right? Because this one is in the wait stage. And this notify, and this one gets into the acquire stage. And I release, and one of them will acquire it first, depending on which one acquired first. If this one acquired first, acquired again, then we'll wait for this, turns -1, so it's no good. So this one in the wait stage, so it release, and this one get acquired. Yep, I think this shall work. All right, let's see. Yep, I think this is correct. Go for it. Yeah, look at this, much faster. This is much faster. So this is using, that's not using event. This is using condition, right? Using condition. And we end up with 77 milliseconds, right? It's much faster, 41%. See, that's concurrency is fun, right? Concurrency is fun. All right, now we can check. Oh man, this dude is the same dude on barrier. Oh, barrier is. Yeah, we got the condition. Event. Slightly different. Oh, we have a first one set here. But it's fine, we figured it out. The lock will be the same, semaphore will be the same. Oh, that's the barrier. Okay, so barrier says they have to be, everybody has to wait in order for the threads to go on. Let's see barrier. So barrier says each of the threads tries to pass the barrier by calling wait, and will block until all of the threads have made the wait call. So all of have to make the wait call in order to proceed. So what are you saying here? So I have 2 threads, right? And then whoever comes in, this one will wait, and this one will print, and boom, they are both calling wait, and then they will go to the next iteration. Ah, yes. If I go to the next iteration, so this is waiting here, right? So they both go if bar is scheduled later, right? Yeah, I don't think this is right. This might pass the online judge. I don't think this is right. What if I schedule full first, right? And then bar, and then full again, right? If we do, no, not full again. Hold up. So wait, right? And then come here. So it's wait here and wait here, right? And then if full goes first, it will print and it will wait. It will get blocked here. And then bar will be, and then bar comes in. And when we go, yeah, that is the problem, right? Because let's say full is waiting, and bar gets run, and it calls wait. So both wait and both do the next thing. So full to the next thing, bar to the next thing. That's the racing condition, right? We need to. Well, we don't know which one will go first. It could be this is faster. I mean, technically speaking, because it's in a loop, so this will this is going slower compared to this, most likely. Well, what if this one goes a little bit slower and this one goes a little bit faster? No. What if this one goes a little bit slower from this statement to this statement? It's slower compared to from this statement to this statement. Now we have two printful, right? And then print this. Yeah, I think both threads reach the barrier. We could have the full thread proceed to the next loop. I agree with this. Yep. It's deterministic. Not guaranteed that a full thread won't run against. Yep, all of these upvote. All right, so we done the condition, right? And we done on the event, but look at the event. So we have two events. We have two events. So bar event dot set. So here we say we wait for the bar, and here we wait for the full printed bar printed. So bar printed is set comes in. Yeah, initial is false, so we set this, right, and then comes in. We wait for bar, yes. Then here we clear, so we wait for this, and then we clear this, so that we can wait again. We print it, and now we say footprint offset. That's nice, good. All right, how about the lock? We have two locks. So bar lock acquire, and everybody want to say I'm acquire my lock, and I acquire bar lock because it's acquired, so this one got blocked. So full lock I can acquire. I do this and then release the bar, and the bar gets released, print it, and now I release the bar. I acquire, so I have the full lock, right? I have the full lock. I'm locked. Hold on. Are you saying if I acquire the lock and I will try to acquire it again, I'm gonna get blocked? I think that's what it's saying. Hold on. Does the documentation say anything about this? And another thread changes to unlocked. So I can call it multiple times. I think that's the case. The same thread can acquire the same lock multiple times, more than once. All right. If the first time I acquire it, and I acquire it again, and if the lock is not released, then I block myself. Right. This basically block myself. So I got blocked myself. So first acquire I can get it, and this acquire will not get it because I acquire it here. And then this got blocked, this is not blocked, and then I release the bar lock, and then I got blocked by myself. And then bar lock release a print, and I release the full lock. All right. So I release the full lock. So this got release. Let's see if there's any erasing. So I'll print and release this. And then come back. So when I release the full lock, it's guaranteed that I will get blocked. It's guaranteed I'll get blocked after, before it gets released, right? Because I release the full lock, okay, and the full lock is released. Yeah, because the print happens before the bar lock gets released. So whatever happens, this one always gets released after the full was printed, right? Yeah, that's the case. I will always print full before I can get released. So whenever I get, think about the state, right? So what will the state of full function be when bar is released? When the bar lock is released? Well, when bar lock is released, I already printed full. That's true. And semaphore is the same, I think. It's the same, which means full can get it immediately and bar gets blocked. Okay, let's try it. Let's just write it. It's fun, huh? I think this is how it's going to be. Every single question when you try to use all of the tools. So this is going to be, we have event, we have conditions, this is using lock. So when I have, I like how he do full printed equals threading.lock, right? And then self.bar printed equals threading.lock. And then his initial is full printed dot release. No, dot acquire. Because full is not printed yet. So I want to come in with self.bar printed. Right? When bar is printed, then I can print full. And after I print full, I can say self.full printed. No, I can just release. Right? Because this one will be self.full printed. But full print is acquire, IRE. So acquire here, so this will get blocked. This one will not block. And then when it goes out, it will release bar. It will release bar printed, but it does not release full printed. So I shall say self.full printed.release. Right? And then this one comes in, will print bar. And after print bar, and I say self.bar printed.release. All right, let's analyze it. So initial full printed is locked, right, which means it's not printed yet. But bar printed is not locked, which means bar is printed. Therefore, this one gets blocked. This one goes in, print full. And if I print it, I say, okay, full printed, I can release it. So I release this, and this will go, right? And then I come back, I'll get blocked here because I released the bar. Hold on. I release the bar. I shall not release bar. Bar can only be released by bar. No, I have just to call to acquire. I cannot release bar. I need to acquire. and then .acquire. I cannot release. Right, the release can only be like full printed can only be released by full. Bar printed can only be released by bar. Right, and then bar released, and the full release, this goes in, and then bar is not released until print bar. So I think this one's right. Using lock. I got 3. That is 3. Okay. 2, 10. Yep, and this is correct. And last one, semaphore. Semaphore is the same. Same as lock. So this one will be using semaphore. Right, using semaphore, same thing. There's going to be semaphore. The full printed will be 1, because full needs to be acquired. Bar printed, semaphore 0, right? And then we can say, oh, the rest is the same, I think. Same idea. Nope. I think I got it backwards. Nope. Full 0 is locked. 1 is not locked. So I think I got it backwards. 0 is locked. 1 is not locked. There we go. Okay, this is semaphore. Oh, wow, semaphore is even faster. What else? What else? 5. Barrier. No, we don't do barrier. Yep. Acquire. Yep. All right, that's it. All right, that's it for today. We didn't do very well on the easy question. Damn. I'll see you guys tomorrow. Adios.